Hey guys, how's it going? So in this tutorial I'll be showing you guys how to calculate the equation of state and hence the bulk modulus, equilibrium energy as well as the equilibrium volume using quantum espresso and CrysX. So a while back I wrote a post on bulk modulus calculation using quantum espresso and it is doing pretty well even on search engines. So I just thought I might as well make a video about it explaining this procedure in a greater detail. So the thing about equation of state is you must have seen in a variety of literature something like this. So basically what they do is they calculate the energy of your system at different volumes and then fit it to some equation of state and then calculate the bulk modulus, equilibrium volume, which would be basically the minimum of this parabola, as well as the equilibrium energy. So there are a variety of equation of states that are used for this purpose. So the most popular ones are Murnaghan equation of state. So you can find the Wikipedia article about Murnaghan equation of state here, and it is basically given by this expression. So this expression basically gives you a variation of energy with respect to equilibrium volume, EV naught. Then B naught would be your bulk modulus, B naught prime its derivative, then V would be your volume, V naught would be the equilibrium volume, and so on. So this is the Murnaghan equation of state. And another equation of state which is pretty popular is Birch-Murnaghan equation of state and a Rose-Vinet equation of states, and so on. So in this tutorial I'll be showing you guys how to calculate all these equation of states as well as these equilibrium energy, equilibrium volume, and the bulk modulus using quantum espresso. So the first thing that you have to do is you have to find out the materials. So for the sake of this tutorial I'll be using the iron, which is a basically BCC structure. So let me see. Okay, so here it is. So here's the Wikipedia page of iron, which basically tells us that iron has a BCC structure at a room temperature, and it has a bulk modulus of 170 gigapascal. So we'll be running a very rough calculation using quantum espresso and see if we can get something like this or not. So the first thing that we need here is we need the iron crystallographic information file. So just go ahead and run iron CIF file and search for it using your favorite search engine, and then go to this link that is AMCSD search results. So here you can see you have iron, and then this is the one we are looking for. So just go ahead and click on download CIF data, and then just go ahead and save this CIF file anywhere that is accessible to you. I'll just save it on my desktop and call it FE. Now the next thing I need you to do is you need to launch BURAI. So I have already made several videos on BURAI, which is a GUI of quantum espresso. So here it is. So what you can do is you can go to my computer and search for your desktop or wherever you downloaded that file. So I downloaded mine to my desktop, and I'll just go there and open that fe.cif file. So in order to calculate the equation of state, I already told you guys you will need to run the SCF calculation at a number of volumes. So I mean, I didn't tell you this exactly, but I told you that you would need the value of energy at a bunch of different volumes. So all these green dots are the energy at different volumes. So you'll need that, and then you will be fitting some equation and then getting that equation of state parameters. So how to do that would be pretty easy using BURAI. So what you can do is you can see that currently the lattice parameter is 2.866 angstrom. So in order to change the volume, which is a cube right now, you can basically just change this and the volume will change itself. However, before you do that, the first thing you have to do is you need to change this to crystal. So you will be needing to providing the atomic positions in crystal coordinates rather than atomic positions. So now if you will have a look at the input file, then it will be atomic positions crystal and the Fe atom at the origin, one Fe atom at the origin and the other at the BCC, and all the rest are its images. So that's it. So now if you go ahead and change the volumes, so let's say you start your calculation from 2.78 to 2.98. So let's say I'll be changing my volume from 2.78 in steps of 2 to 2.98. So I'll be changing this volume in steps of 0.02 from 2.78 to 2.98, and then I'll be calculating the equation of states. So I'll be calculating volume for I will be calculating the energy for volume 2.78 cube, for 2.80 cube, for 2.82 cube, and so on. However, since we have already provided the atomic positions in terms of crystal coordinates, they will not change when we change the lattice parameters. However, had we provided these in angstrom coordinates, then that would have been a problem, because if we would change this but the atomic position will remain the same, then there will be problem. For example, let's say we are already in angstrom. Okay, so now as you can see, since it was 2.98, so it easily knew that the second Fe atom would have to be at the half of that, that is 1.49. However, if now I change it to 2.4 or something like that, now you can see that this atom is no more at the center. So that is the thing, that is the precaution I was talking about. However, so just go ahead and change it back once again. So just make it 0.5 5, and then change it to 7, 8, and then go to the SCF, and then just change these to yes. Increase the cutoff to, let's say, 40 Rydberg. So however, you have to perform a convergence criteria test on this, and I've already made a video about that, so you can check it out. However, for this rough calculation, although we want some decent results, so I'm taking 40 Rydbergs and just change it to 6 by 6 by 6, I guess. Let the smearing be on and the smearing be Gaussian, and then magnetization is on. Okay, so now if you will go ahead and check out this input file, so that is pretty much okay for a rough calculation. So just go ahead and copy all this, launch your favorite notepad text editor. No, okay, and then just paste all this and save it by some name. All right, so I have already gone ahead and created several input files, that is scf1.in, which has the lattice parameter as 2.78, so the volume would be its cube. Then I have another input file that has the lattice parameter as 2.80. Then I have another input file which has the lattice parameter as 2.82, and so on until the last input file which has the lattice parameter as 2.98. So I've already created a bunch of input files, and then what you can do is you can basically launch your command prompt, and let's see. Okay, so we are here in desktop and Modulus. All right, so just go ahead and run your calculations. So I have the pw.exe direct executable address here, and then the name of the input file, and then the name of the output file. Okay, so it was scf1.in, and then just go ahead and hit on enter. However, to save some time, I have already run the calculations, as you can see here, scf1.out, scf2.out, scf3.out. However, I'll show you that it doesn't take a lot of time. It just takes a few moments to run this basic calculation. So let me see here. Okay, so it is already completed. I'm not sure what this is going on about. Okay, I just hit enter there, and as you can see, it was completed right now. 21:53:49 is 21:54. So I'm not playing with you guys for some reason. This didn't register the job getting complete. However, now what you can do is you can run all these input files like this, and then you will have a bunch of output files like scf1.out, scf2.out, scf3.out, and so on. So the next step, what you need to do is you need to take a note, or compile the energies versus the volume. So first, just go ahead and search for a line that contains an exclamation mark with total energy, and that would be your total energy. So just go ahead and each file and search for this thing, similarly here, and similarly in all the other files. So you'll just open these files, search for this output, that is exclamation mark 4 spaces total energy. So you will search for that. So now you have a bunch of energies here. So let's say you opened Excel. So here I have already compiled the volumes, the lattice parameters, that is 2.78, 2.8, 2.82 and all that up till 2.98, and then here I'll just cube them to get the volume. So here so here I have the volumes with me, and then the next step I need to do is, so basically I used Excel because it was pretty easy to get the volumes in a single step. And then basically just open your favorite notepad editor and text editor, and then just copy all these volumes in this row. So here I have copied all those volumes, that is the first column is of the volume, and then you will have to note down the energies. So this was the first energy, SCF1.out, and then copy it into this file. So just provide a tab and then copy that. Similarly from SCF2, so you have this one, 111.604789. Yeah. So as you can see, I have done almost all the work beforehand. However, this doesn't mean that I'm playing with you. You can see that each and every calculation is corresponding to the what I'm showing you on the screen. So once you have a notepad file or a .txt file which has the columns in the first column and the corresponding energies in the second column, then it is pretty easy to calculate the equation of state either by using Quantum Espresso or by using my app CrysX. So this CrysX is a mobile Android app that can also be used to calculate a variety of equation of states. However, let's just see how to calculate the equation of state using Quantum Espresso first. So similar to the previous step, you will need to provide the address of the Quantum Espresso executable called ev.exe. So in the previous step we were using pw.exe, however this time we'll be using ev.exe. Similarly, Linux users will be writing ev.x here. So just type out the address and click enter. So you'll be executing ev.exe file. So once you execute that, it will prompt you to enter whether the lattice parameters or the volume are in atomic units or angstroms. In my case these are in angstroms, so I'll just write in G, then enter the type of Brovell lattice. So in my case, although it is a BCC lattice, however, since I have provided the volumes in the first column rather than lattice parameters, so if you are using a cubic lattice and provide lattice parameters in the first column, then you can choose FCC, BCC, SC, etc. However, since I have provided volumes, I'll just click here and enter non-cubic, and then it will ask me which type of equation of state I want. So I'll just go ahead and click on Mornagan and hit enter, and then it prompts me to name the input file. So input file, as I already told you, should be something like this, with the first column having the volumes, the second column having the corresponding energies. So just type out the name. However, please make sure that you are in the same directory in which this input file is. So currently I'm in the same directory, bulk modulus FE. So if you open that, you will notice that I have this file volume versus E_FE, that is this one. So I'll just type out the name vol vse_fe.txt. So just type out its name, and then the name of the output file, let's call it EOS final, and hit enter. So here you will notice that now you have a file called EOS final. So just right click on it and open it with your favorite text editor, and you will notice that now you have an equilibrium volume that is 23.12 angstrom, bulk modulus and GPA that is 154.3, which is not very close to this given on Wikipedia page, that is 170. However, I've noticed here that other people have gotten 1.73 using DFT, so maybe maybe there's something we can do about it by increasing the cutoff energy of plane waves, as well as the charge density, as well as the your k-point mesh can be done. So we have got the, so this is the output file that basically gives the equilibrium volume, bulk modulus, derivative, first derivative of the bulk modulus, second derivative 0, equilibrium energy. So all these parameters basically spell out the equation of state for you, which is this one. So now you have all these parameters as well as the equation of state. So that's how you will be calculating bulk modulus using quantum espresso. However, you can also calculate bulk modulus using my app, that is CrysX by PhysVis. So in order to do that, what you'll need to do is you need to download the app, which is available on the Play Store by the name of CrysX crystallographic tools. So just go ahead and download this app and run it on your Android phone. And also you can either enter these manually into the app, or you can also just go ahead and copy paste this file, as the application can also read this file, similar to Quantum Espresso. So just launch the CrysX crystallographic tools application on your Android smartphone and head on to the sidebar menu and go to the EOS fitter. So once you are in this EOS calculator, then you can either enter the value of the volume manually like this, 21.4845, submit 21.952. So in this way you can enter the volume values, and similarly you can enter the corresponding energies by double clicking here. So you will get minus sign, then 111.6024, done, and then minus 111.60478, submit. So in this way you can enter the value of the volume as well as the corresponding energies manually. However, you can also read .csv and .txt files, and the txt files are basically in the same format as read by Quantum Espresso. So we'll be able to read the same file that we created a little bit earlier. So just go ahead and copy that file onto your smartphone and hit on read.txt, and then provide the necessary storage permissions, and then go to the volume versus e_fe.txt, which is the file we just created, and it has basically the volume in the first column as well as the corresponding energies in the second column. And then just go ahead and tap it, and you will see that it will be able to read all these values automatically. And then just go ahead and click on calculate, and you will get the Monaghan equation of state, Birch-Monaghan equation of state, as well as the Wiener equation of state, along with a useful graphical representation. And you have the equilibrium energies, bulk modulus, volume, derivative of bulk modulus, which are all in very good agreement with the values that you're going to get with Quantum Espresso. It's no big deal here. And then you can also go ahead and share this graph by clicking here, and that's it. I hope you guys really enjoyed this video and learned something new. In case you did, then don't forget to hit the like button and subscribe to my channel for more videos like this. Thanks for watching, and have a great day.